Hello, welcome to this video. So in this video I'm going to be covering more quantum field theory for the gifted amateur. I made a version of this video last night, but I was rather tired, and so there were a few things which I wanted to kind of correct from that video. Now I'm more awake, and so this video, for those who are new to it, will cover the equation of motion for four-dimensional fields in space-time, where this equation of motion will build on Hamilton's principle of least action, which we looked at last time. And it's these kind of four-dimensional fields which are the fields we quantize in quantum field theory. So they're very important. So this is an overview of quantum field theory, where we'll be looking at the Euler-Lagrange equation and how it applies to particles, and how a version of this can also be applied to quantum fields. So our starting point. So for this video, I'm going to assume you're familiar with the Hamilton's principle of least action, or at least have seen a bit of it from either previous books, previous YouTube videos, or maybe even part 3 of quantum field theory for the gifted amateur, which was the last video I did. So the principle of least action can be summarised by saying that a particle, or as we will soon find, even a field, has an equation of motion, and for a particle this equation of motion will be how its position changes with time. So for example, a function like x of t, the function x of t will be a function such that the functional, or the action, will be minimized. So we say the functional derivative of the action with respect to position is equal to 0. And we'll treat this as our most fundamental equation. But this equation so far isn't really very useful in this form, even though it's very compact, and in this sense rather beautiful in terms of the amount of things that follow this single equation. We would ideally like to look at this equation in terms of something which relates more directly to the physical universe than the abstract concept of an action. And so this is where we define the action to be an integral of the Lagrangian. And remember, the Lagrangian relates to the kinetic and potential energies of our particle. So the Lagrangian is firmly rooted in things that, if we cannot measure directly, we can very easily calculate from things we can measure and things that are very familiar to us. Because the Lagrangian is based on types of energy which we're rather familiar with. So this is our classical starting point. Now what we're going to be doing is using these two things to derive an equation of motion which isn't quite as fundamental as talking about the functional derivative of the action, but is fairly fundamental and is called the Euler-Lagrange equation, and is an equation of motion for the particle in terms of the Lagrangian. So we start off with the top two equations, which we assume to be true, where we're saying that the functional derivative of the action with respect to the position function is 0, and that the action is defined as the integral of the Lagrangian over time. And also, because the Lagrangian will depend on kinetic energy and potential energy, it is worth saying that we can assume pretty much all the time that Lagrangian will be a function of position and velocity, or in other words, position and the first time derivative of position. And the first time derivative of position we represent as x with a dot above it. And we can assume that this is usually always the case, because the Lagrangian depends on kinetic energy and potential energy. Kinetic energy is a function of the of x dot, and the potential energy is almost always just a function of x. In some very strange situations, it might be a function of x and x dot, such as if we're looking at kind of particles moving in magnetic fields. But in virtually no situations will it be a function of x, x dot, and dash or, and x dot dot. That is, the potential energy will very rarely be a function of acceleration. So because of that, we can assume that in pretty much all the cases we'll encounter, the Lagrangian is a function of x and x dot. So using the top two equations, one can show, and the book goes into detail on this, that we can derive the Euler-Lagrange equation. And this equation just comes from the top two equations by substituting one into the other and then doing relevant usage of functional derivatives, and also a bit of the chain rule from what you would have seen when doing ordinary differentiation if you've done A-level maths or beyond. So the Euler-Lagrange equation is essentially Hamilton's principle of least action, but just for the special case where the Lagrangian is a function of x and x dot. But as I've argued, the Lagrangian is almost always a function of x and x dot. So we have our fairly fundamental equation, the Euler-Lagrange equation. But it's worth saying that in this equation, I've assumed that the position of the particle is represented by x, so the particle is moving in, say, one direction in space. However, generally, we might want to describe the position of the particle in terms of its angular position, so we might want to use an angle instead of an x-coordinate. And because of this, we usually replace our x's with something called generalized position, q, where q could be any description of position we like. So it could be position along the Cartesian axis, such as x. It could be angular position, such as theta. It could be many things. And using a generalized position, the Euler-Lagrange equation is as shown here. Now, it's worth saying that since L is a function of q and q dot, we can kind of forget that q and q dot are themselves functions, because they're functions of time, because they vary with time. But because we can ignore this, we can kind of think of L as a function in terms of just two coordinates, q and q dot. And in this way of thinking of it, the functional derivative, it becomes replaced by the partial derivative, and therefore we have the last equation, which is usually what the Euler-Lagrange equation is shown as. So what we have here is a very general Euler-Lagrange equation where we've assumed something about the nature of the Lagrangian, which we can fairly easily justify. We replaced x with generalized position, and lastly we noted that we can think of q and q dot as coordinates as opposed to functions, and in this instance the functional derivative becomes the partial derivative. So we have, from the previous slide, a equation in motion for a particle in terms of generalized position, and we called this equation the Euler-Lagrange equation. Now we want something similar for fields. Now, for fields or extended objects like strings, because they're spread out, the kinetic energy and potential energy becomes integrals because they're spread out over space. And that's important because the kinetic energy or the potential energy of a field or a string at one particular point in space is infinitesimal, because kinetic and potential energies are spread out over the field or the string or whatever extended object we're dealing with. Therefore, we replace the Lagrangian with something called the Lagrangian density. And as the name density might kind of suggest, we get back the original Lagrangian by integrating the Lagrangian density over space, in the same way that we get kind of the mass of an extended object by integrating its density over space. And the neat thing about this is, because the action is the integral of the Lagrangian with respect to time, we can say that the action is also the integral of the Lagrangian density, but over all our kind of space-time coordinates. And so we can think of essentially the action, which gives a value that we're trying to minimize to find the equation of motion. We can think of the action as kind of like the Lagrangian, but over the entirety of space-time, in that the action we get by integrating the Lagrangian density over the entirety of space-time. And it's worth saying the curly L is the Lagrangian density, but because in quantum field theory we only really use the Lagrangian density, we don't use the Lagrangian, particle physicists and theoretical physicists have often just called the Lagrangian density the Lagrangian, and I'll probably do this quite a few times throughout these series of videos, but it's just worth highlighting. Physicists like to shorten things, but technically there is an important distinction between the Lagrangian and the Lagrangian density. But they work in very analogous ways in terms of the equation of motion. It's just when we're finding the equation of motion for a particle, we use the Lagrangian. When we're finding the equation of motion for an extended object, we use the Lagrangian density. Now, our field will also likely have derivatives across time and space. And because of that, the Lagrangian density is a function of the field, but also the derivatives of the field. And you might here notice that the derivatives of the field are given in terms of the four-dimensional gradient operator. We mentioned in an earlier video when we were talking about covariant and contravariant vectors. So we need to bear that in mind, that we're dealing with the field, but also all derivatives of the field across space-time. Now, we now propose that a field obeys a very similar equation to the equation of motion for a particle, which is the Euler-Lagrange equation. It's just now we replace the Lagrangian with the Lagrangian density, and we also replace derivatives over time with our four gradient, if you like, or our four-dimensional derivative operator. And that way we get something that we can also call the Euler-Lagrange equation, but for fields. And it looks something like this. So it's very similar to the Euler-Lagrange equation for particles, just now this works for extended objects in space-time. And when we've used the 4 gradients, I have explicitly assumed that the field exists in 4-dimensional space-time. So this is kind of the central equation of motion for the kind of fields we deal with in quantum field theory. In a later video, we'll look at kind of different Lagrangian densities that different fields have to give us an idea for the kind of quantum fields that we want to quantize. But we'll probably park the discussion of Lagrangian densities and equations of motion here, and next time we'll be looking at building ideas of how we describe particles by quantizing things in quantum mechanics. And then in later videos we'll look at quantizing fields themselves. So I hope you liked this video. If you have, please check out my other videos for more on quantum field theory.